Welcome to the explainer. Picture this, you're merging onto the highway, you put your foot down and suddenly, bam, you feel that exhilarating surge of acceleration push you right back into your seat. That, my friends, is the absolute magic of what we're talking about today. We're breaking down the extreme engineering of turbochargers and, spoiler alert, the staggering costs of ignoring their maintenance. If you've ever wondered how that little device under your hood manages to squeeze so much power out of your engine, or why mechanics physically wince when one goes bad, you are definitely in the right place.
Okay, so here's our roadmap for today's explainer. We're gonna cover 1. How turbochargers actually work. 2. Twin scroll and VGT tech. 3. What kills a turbocharger. 4. Symptoms of turbo failure. 5. The big question, repair, rebuild, or replace. And finally, 6. Preventing catastrophic turbo failure. Let's get into it. Starting right off with Section 1, how turbochargers actually work. We really need to nail down the baseline engineering to understand exactly what a turbo is doing before we can fully grasp why they break. At its core, a turbocharger allows an engine to burn more fuel with far greater efficiency. By forcing a highly compressed charge of air into the combustion chamber, you don't need to increase the physical size of the engine block to get a massive boost in performance. The true genius of this device is that it's basically capturing waste energy. Instead of just blowing hot exhaust straight out the tailpipe, it actually harnesses that escaping pressure to spin up a compressor. So it's essentially giving you free power harvested directly from the engine's own exhaust gas. Now, think about the division of labor inside the unit. The turbo is basically split right down the middle into two distinct halves. The hot side handles the high-velocity exhaust gases pushing out of the engine, while the cold side acts as the compressor, sucking in fresh air and feeding high-pressure air back in. The thermal dynamics happening here are literally insane. You have absolute extremes in temperature separated by mere inches of metal. On one side, superheated exhaust is blasting through, while right next door, cold ambient air is being drawn in and compressed. So how does this continuous high-velocity airflow loop actually work? Well, it's a pretty elegant step-by-step process. First, exhaust gas exits the engine block. Second, that gas forcefully enters the hot side and spins the turbine wheel. Third, because that turbine is physically connected to a central shaft, it instantly spins the compressor wheel over on the cold side. And finally, that spinning compressor pulls in fresh ambient air, pressurizes it, and forces it right back into the engine intake. It creates this beautiful feedback loop that delivers that signature, thrilling boost in power. To put this extreme engineering into perspective, the internal shaft connecting those two sides spins at a mind-blowing 240,000 revolutions per minute. Just try to visualize that speed for a second. 240,000 RPM. At that speed, traditional steel ball bearings would instantly melt and disintegrate from the friction, no question. To survive this, the central shaft doesn't use standard bearings at all. It actually floats on a microscopically thin, highly pressurized layer of engine oil, basically hydroplaning continuously while the engine is running. Now, couple that intense 240,000 RPM speed with exhaust temperatures reaching up to 950 degrees Celsius on the hot side, it is a literal glowing inferno in there. The only things preventing a complete and catastrophic meltdown are specific liquid coolant and oil channels actively wicking away that 950-degree heat. If those fluid channels are interrupted for even a fraction of a second, the metal would literally warp and fuse together. Moving on to Section 2. Twin scroll and VGT tech. To maintain efficiency across different engine speeds, engineers had to develop some pretty brilliant workarounds. Take the twin scroll system, for example. A twin scroll physically separates the exhaust pulses from different engine cylinders into two distinct channels. This completely prevents the exhaust waves from colliding and interfering with each other. It keeps the flow incredibly smooth and drives the turbine much more efficiently. But this brings us to a major engineering challenge. How do we get the turbo to spool up fast enough when the engine is only producing a low volume of exhaust gas at low RPMs? I mean, we've all felt this out on the road, right? You put your foot down to pass someone and you wait a frustrating 1 or 2 seconds before the power suddenly hits. If the turbo just has one big opening, the exhaust gas moves too sluggishly to spin that turbine quickly. And that right there is the dreaded turbo lag. So engineers solve this lag issue with variable geometry turbos, or VGT. By electronically adjusting internal vanes into a small gap position at low RPMs, it acts exactly like blowing through a thin straw. Think about it. If you blow air through a wide pipe, the air is slow, but pinch it through a straw, the air velocity skyrockets. This accelerates the gas, spinning the turbine instantly and eliminating lag.
As engine speed increases, those internal vanes automatically open up wider to slow the gas velocity down and prevent overboosting. It's an incredibly elegant mechanical ballet happening thousands of times every single minute.
All right, section 3. What kills a turbocharger? We're transitioning now from pristine engineering to the harsh, friction-filled realities of what actually destroys these robust devices out in the real world.
The main culprits here are almost always related to neglected maintenance. First up, you have contaminated oil, which acts exactly like liquid sandpaper, relentlessly grinding against a shaft that is spinning at 250,000 RPMs. Then you've got oil starvation from blocked lines, which causes those bearings to instantly overheat and weld together. And finally, there's foreign object damage, or FOD. If a cheap air filter breaks and lets even a tiny pebble through, that pebble strikes the hyper-spinning turbine blade like a literal bullet, shattering the internal fins entirely and destroying the unit on the spot. Which brings us to section 4, symptoms of turbo failure. The really good news here is that your car will clearly communicate these internal failures long before catastrophic engine damage occurs. Well, that is, if you're actually paying attention to the warning signs. Diagnosing these signs correctly is absolutely key. If you hear a loud whining or grinding noise under acceleration, honestly, it sounds a lot like a dentist's drill, your internal bearings are actively failing. Next, if you see excessive blue or black smoke pouring out of your exhaust, that indicates your internal seals have blown, and raw oil is leaking directly into the extremely hot combustion chamber. And finally, if you experience an engine misfire, a rough idle, or a sudden loss of power accompanied by a check engine light, your turbo is sending out an absolute SOS. As automotive expert Steven Jackson warns, ignoring these warning signs is a massive gamble. When the turbo leaks oil into the intake or shards of a Schotter turbine fly directly into your engine block, you can destroy your entire engine. It's a ticking time bomb. After a cylinder misfire or smoke from the exhaust, there is absolutely no way of knowing whether the engine will give out in a few days, a few hours, or just a few minutes. Section 5, repair, rebuild, or replace. Let's talk about the hard financial realities of getting your vehicle back on the road safely once a failure has actually happened. Let's break down these cost differences. A rebuild, sitting in that 195 to 1,400 pound range, is highly viable and cost-effective if you just have moderate wear to the internal bearings or seals and the main core housing is totally intact. But if you've suffered severe damage, we're talking broken turbine blades or cracked housing, you are looking at a full replacement starting around 550 pounds for a small hatchback. And if you have a twin turbo or high-performance setup, oh boy, that replacement bill can easily skyrocket well past 4,000 pounds. When it does come time to replace, our sources strongly recommend sticking with original equipment manufacturer, or OEM parts. Car manufacturers put massive amounts of R&D into the exact tolerances of these turbos. Cheap aftermarket turbos might look super tempting to save a few bucks up front, but it is a dangerous false economy. Their quality varies wildly. Poor fitment and slightly off tolerances will quickly lead you right back to the mechanic with yet another blown turbo. Just don't do it. Finally, Section 6, preventing catastrophic turbo failure. Let's empower you with some simple preventative steps you can take starting today to avoid these massive repair bills altogether. Frequent, high-quality synthetic oil changes are your absolute primary defense here. Fresh oil keeps those internal bearings floating and the extreme core temperatures down. You also need to keep your air filters consistently clean so no rogue debris shatters your turbine. Maintain your engine's cooling system, and crucially, avoid letting your car idle excessively. Excessive idling without proper airflow builds up immense carbon and heat stress inside the turbo housing, literally baking the oil into a thick, damaging sludge over time. As we wrap up today's explainer, I want to leave you with a final thought to ponder the next time you think about maybe skipping your scheduled vehicle service. Is putting off a simple, inexpensive oil change really worth gambling on a 2,500-pound, multi-4-figure engine rebuild? Treat your turbo right, give it the clean oil and fresh air it so desperately craves, and it will effortlessly deliver that smooth, powerful boost for years to come. Thanks for joining me on this deep dive.